Hi everyone, my name is Sanjay. I'll be going over Physics 172, Fall 24, Exam 2. So problem 1 states, a planet moves in an elliptical orbit around a star located at X. What is the sign of incremental work, W, done by the star on the planet as it moves at various points in the orbit? So the first thing I need to do in this case is identify our system and surroundings. So our system is our planet, and our surroundings are the star at X. Now that we have that, we can say the change in energy of the system is equal to the work surrounding. So we have kinetic energy plus potential is equal to work done by our star. In this case, there'll be no potential energy. So now we need to recall our definition of work. Work is equal to the dot product of the force times the change in position, or it can also be written as F times the change in position times cosine theta. So we have three general cases. If theta is less than 90 degrees, cosine theta is greater than 0. If theta is greater than 90 degrees, that means cosine theta is less than 0. And if theta is equal to 90 degrees exactly, then cosine theta, or cosine pi over 2, will be equal to 0. Now that we have that, we need to identify three cases in our elliptical orbit. So 1, it is moving away. 2, it is perpendicular. And 3, moving closer to the star. So it's moving away at 1 and 2. It is perpendicular at 3 and 4. And it's moving closer at 5 and 6. So let's do our three general cases that we have here and draw on our gravitational force and change in position. So at 3, we have force of gravity acting inward. We have our change in R. And we have our theta is equal to 90 degrees since it's perpendicular in this case. So theta is equal to 90, which will imply to us that work is equal to 0 because cosine theta is equal to 0, and that means work is equal to 0 at points 3 and 4. So right away we can cross out answer choices C, B, and E. It leaves us with A and D. Our second case, which will be moving closer, let's do point 6. We have our gravitational force acting inward. We have our change in R. And we have our theta. You can say theta in this case is less than 90 degrees. So we can say theta is less than 90 degrees implies that work is greater than 0 because cosine theta is greater than 0. And this will also mean that it is speeding up. since it's getting closer to the star. And in our third case, let's do point 2. We have change in r, we have the force, and we have our theta. Theta in this case is greater than 90 degrees. So for case 1 where it's moving away, we can say theta is greater than 90 degrees, which will imply to us that the work is less than 0 because cosine theta is less than 0. And this will also imply to us that we are slowing down because the planet is moving away from the star at points 1 and 2 in this case. So after determining our 3 cases, we can conclude that answer choice A best fits our criteria. Problem 2 states, a ball of mass 5 kg is attached to the end of a light rigid rod of negligible mass. You swing the ball in a vertical circle of radius r is 1 meters at a constant speed of v is equal to 7 meters per second. What is the work W done by the rod on the ball as it moves from point C to D as shown in the figure? Assume that the magnitude of acceleration due to gravity is 10 meters per second squared. Select the closest answer. So the first thing I'm going to do in this problem is identify our system and surroundings. So our system in this case will be our ball and the earth. And our surroundings will be the rod. From that, we can say the change in energy of the system is equal to the work surrounding. And from that, we can say the change in kinetic energy plus the change in potential energy is equal to the work done by our rod. We can further write this as 1/2 mv final squared minus v initial squared plus mg times the change in y is equal to the work in the rod. And because we know that speed is constant, we know that v final is equal to v initial. Therefore, our kinetic energy will cancel out in this case. So now to find our delta y, we have our starting point at C. Let's call that start. That is at 0 minus 1 meters. And our point D, which is we'll call end, that is at -1, 0 meters. So when we do the change of y, it's equal to y final minus y initial. We have that is equal to 0 minus -1, which is equal to +1 meters. Therefore, we can say the work done by our rod is equal to our mass, which is 5 kg, times gravity, which is 10 meters per second squared, times our change in y, which is equal to +1 meters. So that will give us an answer of 50 kilograms times meters squared divided by second squared. And that is equivalent to 50 joules. Therefore, that will give us answer choice E. Problem 3 states, a spacecraft of mass 300 kg is in outer space at location 112 meters, moving at an initial speed of 3 meters per second. One set of thrusters are now turned on and exert a constant force of 100, 200, 200 newtons until the object reaches location 2, 2, 3 meters. At this point, the thrusters are now turned off, and another set of thrusters are turned on, which exert a constant force of 200, 200, and 200 newtons until the spacecraft reaches location 3, 3, 4 meters. What is the speed of the spacecraft at the final location? Select the closest answer. So the first thing I'm going to do is identify our system and surroundings. Our system is our spacecraft, and our surroundings are our thrusters. And in this case, gravity is negligible because we are in space. So Earth, will, in this case, will not be a surrounding. Now we can say from this, the change of energy in the system is equal to the work done by the surroundings. We know that the energy of the system is moving at an initial speed of velocity, and we're solving for the final speed. So we have kinetic energy plus potential energy, in this case will be 0, is equal to work, which is defined by the dot product of force times displacement. Once we have that, we can say 1/2 m v final squared minus v initial squared is equal to our work by the thruster. So we can say that the change of R1 is equal to 2 minus 1, 2 minus 1, and 3 minus 2 meters, which is equal to 1, 1, 1 meters. We can say the change of R2 is equal to 3 minus 2, 3 minus 2, and 4 minus 3 meters, which is equal to 1, 1, 1 meters again. And R1 will represent the first thruster, and R2 will represent the other thruster. So in this case, we have F1 times R1, the dot product, plus F2 times R2. And this will be 100, 200, 200 newtons, dot 1 meters, plus F2, which is 200, 200, and 200 newtons, dot 1 meters. And so when we simplify that, we get 1/2. The mass is 300 kg times v final squared minus v initial squared, which is, in this case, 3 squared, which is 9, is equal to, we have to recall the definition of dot product. It will be 100 times 1 plus 200 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 times 1. So we have from that 150 VF squared minus 1,350 is equal to 1,100. So we have 150 VF squared is equal to 2,450. So VF squared is equal to 16.33. And when we do the square root of that, we get that VF is equal to approximately 4.04 meters per second. And this will correspond to answer choice D. Problem 4 in PHYS state, an ice block of mass m is initially at rest at location 1 on a smooth circular track in a vertical plane. It is let go and slides down the track. Acceleration due to gravity, g, is downward. Ignore air resistance. Part A, what is the speed of the block at point 2? So first thing I'm going to do to solve this problem is identify our system and surroundings. Our system, in this case, I will choose the block plus the earth. And our surroundings will be nothing. And now that we've identified that, we can say that the change of energy in the system is equal to the work surrounding. And in this case, it will be equal to 0. We can rewrite our change in energy of the system equal to the change in kinetic energy plus the change in potential energy is equal to 0. We can also rewrite this as 1/2 m v final squared minus v initial squared plus mg times the change in y. So since we are initially at rest, we can say that v initial is equal to 0, and our v final is unknown, and that's what we're solving for in this case. And another thing we need to do is identify our coordinate system. So we have positive x and positive y. And so let's suppose I draw a dashed line here. And at this point, at the very bottom, let's call that the origin 0, 0. So from that, we can say that our y initial is equal to the radius of our circle. Y initial is equal to r. And our y final is equal to 0. Therefore, we can say the change in y is equal to y final minus y initial, which is equal to negative r. So, rewriting our expression after solving for this, we have 1/2 m v final squared minus 0, since initial velocity is 0, plus mg 0 minus r is equal to 0. We can also cross out the masses on both expressions. So now that we have that, we can say 1/2 vf squared minus gr is equal to 0. And from that, in terms of final velocity, we can say vf is equal to the square root of 2gr. And this answer will correspond to answer choice D. Part B states, what is the magnitude of the normal force Fn on the block by the track at point 2? So I will draw a free body diagram, and before I do that, I'll define our coordinate system. In part A, we define this as positive x and positive y. So we have our FBD at point 2. So we have our block, and from the center of mass, we have our force of gravity acting downward. I'll call that mg. We have our normal force acting upward. We'll call that Fn. We also have centripetal acceleration acting upward. And in this case, centripetal acceleration will act upward because it always points towards the center when we're doing a circular motion. And we can define centripetal acceleration AC as equal to the velocity squared over the radius, v squared over r. And so from all of this, we can say the sum of forces in the y direction is equal to mass times acceleration from Newton's second law, and that will be equal to mv squared over r. And from that, we can also say Fn minus mg is equal to mv squared over r. And recall from part A, the velocity at 2 is equal to root 2gr. So we can rewrite our expression for Fn equal to mg plus mv squared over r, which is equal to mg plus m times root 2gr squared over the radius, which is equal to mg plus m times 2gr over r, and the r's will end up canceling in this case. So you can further write that as mg plus 2mg. So that'll give us a final answer that the normal force at point 2 is equal to 3 mg. And that will correspond to answer choice A. Problem 6, 7, and 8 state a block of mass 30 kg is initially held at a certain point on an inclined plane that makes an angle of theta is equal to 48 degrees as shown with the horizontal. The block is in contact with, but not attached to, a spring of stiffness Ks is equal to 1,200 newtons per meters, and compressed length L is equal to 5.0 meters. The relaxed length L naught is equal to 6.0 meters of the spring is also equal to the total length of the incline. When you release the block, the spring pushes it up all the way to the top of the incline, at which point it is launched into the air. The coefficient of kinetic friction between the block and the incline is mu k is equal to 0.3. The magnitude of acceleration due to gravity is g is equal to 10 meters per second squared. So before we solve this problem, I'm going to solve for v naught, our velocity of our block. So in this problem, we're going to say that the system is the block plus the earth plus the spring and the surrounding is the ramp. And you will see this in problem 6 when you are asked to identify which one is correct. So we can say from this that the change of energy of the system is equal to the work surrounding. And from that, we can say the kinetic energy of our block is 1/2 mv naught squared, since it's initially at rest, minus our kinetic energy of our spring, 1/2 the spring constant Ks, times s squared, our displacement, and recall S is equal to L naught minus L, minus our potential energy due to gravity, mg delta y, and visually we'll see that delta y is equal to this distance, delta y, and we'll solve for that later. And that is equal to our work done by the ramp, or friction. So that's mu k times the normal force, but we have to find out the normal force. So let's draw a quick free body diagram. So we have gravity acting downward, we have normal force acting upward, we have our spring force acting to the right, and we have friction acting to the left. And from trigonometry, we can say that this angle is theta. So when we do the sum of forces about the y direction is equal to 0. We have Fn acting upward on our new coordinate system. Call that y prime, and x prime, which is slanted because of the ramp, minus mg cosine theta. So we can say the normal force is equal to mg cosine theta. So we have mu k times mg cosine theta for our force, and then our distance, which is s. We'll call this s. All right, so now that we have that, we can figure out these two distances. We need to figure out this d1 distance and d2 distance, because we know delta y is equal to our final distance of the ramp minus our initial. So we can set up some ratios using some trigonometry. We have sine of theta is equal to d1 opposite over hypotenuse, which is L in this case, and we have sine theta is equal to d2 opposite over L naught in this case. So from that, we can say sine 48 degrees is equal to d1 over L, which is 5 meters. And we have sine 48 degrees is equal to d2 over L naught, which is 6 meters. So we can say d1 is equal to 3.72 meters. And d2 is equal to 4.46 meters. Therefore, we can say that our delta y value is equal to approximately 0.74 meters. And now that we have all our values, we can substitute everything and solve V naught. And so after we do some calculations, we get that V naught is equal to the square root of 21.2. So V naught is equal to 4.6 meters per second, and we will use this for problems 7 and 8. Part A states, 3 students present scientific arguments about finding the speed v naught at which the block is launched into the air at the top of the spring. Which is/are correct? So before we do this, we got to recall that the change of energy of the system is equal to the work done by a surrounding. So let's take a look at the 3 claims. The first one chooses the block as a system and everything else as the surroundings. However, they say that there is change in potential energy from the Earth. That would make Earth as part of the system, which they did not specify. Therefore, this claim is wrong. Let's look at the next claim. They choose the block, spring, and Earth in the system, and the ramp is the surroundings. So they say they have a change in kinetic energy from the block, change in kinetic energy from the spring, and change in potential energy from Earth, and there's also work from friction on the ramp. So that accurately matches what they chose in their claim. So that is correct. The last one, they choose the block and spring as the system and everything else as the surroundings, which is the Earth and the ramp. However, they say that there's work from the spring, but the spring is part of the system and not the surroundings. So that would make this statement incorrect. Therefore, Gada is the only one who is correct, making choice E the correct choice. So based on Gada's statement, we can say the change in kinetic energy of the block plus change in kinetic energy of the spring plus change in potential energy of gravity is equal to the work done by friction. So we have 1/2 m v naught squared minus 1/2 times the spring constant ks times displacement s squared minus mg delta y, the vertical displacement, is equal to mu k times the normal force Fn, which is mg cosine theta, times distance s. And that is what we use in the previous part to derive VO. Part B states, what is the time T max after it's launched for the block to reach the highest point, H max, on its flight? Assume no air drag. Select the closest answer. So I'm going to redraw our ramp and our block M. From the center of mass, we have gravity acting downward, mg. We have our spring force acting to the right. Our impending motion is to the right. And since we know there's friction, the frictional force will oppose our impending motion, so it will go to the left. We also have our normal force acting perpendicular to the ramp. And doing some trigonometry, we can determine that this theta is also equal to this theta. So we have mg cosine theta for the y component and mg sine theta for the x component. And our coordinate system will go from our traditional positive xy to something like this. We'll call it x prime and y prime for a new coordinate system. And once we actually get off the ramp, we have a new free body diagram. So let's suppose this is at its h max. Our only force acting here from the center of mass of our block will be mg. No normal force, no spring force, no friction force because we're in the air. So this is at h max and along the parabola that the path follows. We know that we have velocity, we'll call that v naught. And using some trig, it's the same angle theta. So if we get our vertical component, y component of our velocity is v naught sine theta. So now for momentum. So now to solve for time, we can recall our momentum principle from earlier in the semester. And that is defined by the change momentum of the system, delta P, is equal to F net delta T. And in this case, our system is just our block. So we know it's moving at minus m v naught sine theta minus our initial of 0 is equal to minus mg, because the only force is gravity acting downward, times delta t. So we can rewrite our expression for delta t as equal to, so the m's cancel out, and that will be v naught sine theta over g. So we can plug in our values. We get 4.6 meters per second times sine 48 degrees divided by 10 meters per second squared, and that will give us a final answer that delta t is equal to approximately 0.34 seconds. And this will correspond to answer choice B. Part C states, what is the maximum height, h max, with respect to the top of the ramp achieved by the block? Assume no air drag. Select the closest answer. So now that we're off the ramp, our new system is the block, and our new surroundings is the earth. And from that, we can say the change of energy of the system is equal to the work surrounding. So we have the change in kinetic energy from our block is equal to the work done by gravity. In this case, it's going to be 1/2 m times the change in velocity v naught sine theta minus 0 squared, since we're concerned with the y component of our velocity here. And using some trigonometry, we can determine this theta is equal to this theta here. So that's how you get v sine theta, and that will be equal to mg times h max. So the force of gravity times the maximum height. So when you rearrange that, you get that the m's will cancel out, and H max is equal to V naught squared sine theta squared divided by 2g. And now plugging in our values, we get H max is equal to 4.6 squared meters per second squared sine 48 squared divided by 2 times gravity, so 2 times 10 meters per second squared, and that will give us a final answer of approximately 0.58 meters. And that will correspond to answer choice E. Problems 9 and 10 state, you hold a piece of compressible jello of mass 0.40 kg with a center of mass 0.30 meters above the top of your kitchen table. You let go of the jello, and just before it hits the tabletop, its center of mass has fallen a distance of 0.25 meters. After hitting the tabletop, the jello comes to rest, such that the center of mass of the jello is finally at height 0.02 meters above the tabletop. Use magnitude of acceleration due to gravity as 10 meters per second squared. Part A. What is the translational kinetic energy of the jello just before it hits the tabletop? Select the closest answer. Hint, focus on the transition from the initial point to just before it hits the table. So for part A, we have to recall the definition of translational kinetic energy. And that is equal to the net force, F net, dot the change in position about the center of mass. So in this scenario, our center of mass starts at H and ends at H minus D. So we can say our change in position about the center of mass is equal to R final minus R initial, which is equal to 0 H minus D in the y direction, 0 minus 0 H in the y direction, and 0 meters, which is equal to 0 minus D, 0 meters. And if we draw a quick free body diagram, we see that the only force acting on our jello is gravity, mg. So we can say F net in the y direction is equal to minus mg. So now that we have that, we can say the translational kinetic energy is equal to our F net of minus mg times our y component of the change in position, which is negative d. So that will be positive mgd. And when we simplify that, we get 0.40 kg times gravity, 10 meters per second squared, times our distance d, 0.25 meters. And that will be equal to approximately 1.00 joules. And that will give us answer choice E. Part B states, what is the change in internal energy of the jello? Select the closest answer. And the hint is to focus on the transition from the initial to the final position, both at rest in the figure above. So if we look here, we are concerned with the first one and the third one for part B. We are concerned with figure 2 for part A. So now that we have that, let's identify our system and surroundings. Our system is our jello. Surroundings are earth, our gravity. So from that, we can say the change in energy of the system is equal to the work done by surroundings. So we have translational kinetic energy plus rotational plus change in internal energy is equal to our work done by gravity. Now, we don't have any rotating components here, so we can cross out our rotational kinetic energy. And this is what tricks a lot of people up, and it tricked me too when I took this exam. So the translational kinetic energy will also cancel out to zero because we are concerned with the final state, which is at rest, and the initial state is at rest. So that means the change in velocity is equal to zero. Therefore, K trans is equal to zero also. Don't use your answer from part A in this case. So now that we have that established, we can say the change in internal energy is equal to our work done by gravity. And we know our definition of work is equal to the force times the distance, the change in distance. So we have minus mg times our final position, which is our final is equal to b, and our initial is equal to h. So we have b minus h, which can also be written as mg h minus b. It's equivalent. Therefore, we can say our change in internal energy is equal to our mass of 0.40 kg times gravity, 10 meters per second squared, times the difference of 0.30 meters, the height, h, minus b, 0.02 meters. And when we simplify that, we get an answer of approximately 1.12 kg times meter squared per second squared, which is the same thing as 1.12 joules. And that will give us a final answer of D. A string is wrapped around a yo-yo of mass m and a moment of inertia I. With your hand, you pull the string vertically straight up with some constant force F, such that the center of the yo-yo does not move up or down, but the yo-yo spins faster and faster. When your hand is at a height y0 above the floor, the yo-yo has an angular speed of omega naught. What is the angular speed omega of the yo-yo when your hand has risen to a height of y is equal to y0 plus delta y above the floor? So the first thing I'm going to do is write out our system and surroundings. Our system is our yo-yo, and our surroundings are our hand exerting a constant force upward and the earth exerting gravity. Now that we have that, we can say the change of energy of the system is equal to the work surrounding. And from that, we can say translational kinetic energy plus rotational kinetic energy is equal to the work done by our hand plus the work done by gravity. And we know in this case that the position stays constant, which means our velocity, VCM, is equal to 0 because position, let's call that RCM, is constant. And we know this because it says does not move up or down in this case. So with that, we can say that the translational kinetic energy is equal to 0, and our work due to gravity is equal to 0. So we know by definition that the translational kinetic energy is equal to 1/2 m times the change of velocity squared, and rotational kinetic energy is equal to 1/2 times the inertia times the change of angular velocity squared. So now that we have that, we can say 1/2 times I omega final squared minus omega initial squared equal to mg, and we have some height because our yo-yo has gravity acting downward, and we have our delta y. Delta y is equal to y minus y naught. So we have delta y as our distance. And from that, we can say omega final squared is equal to 2mg delta y when you multiply over the 2, divide by inertia, plus omega final squared. So when you do the square root of that, you get your answer for your final angular speed. So it'll be 2mg delta y divided by inertia plus omega naught squared. And that will correspond to answer choice D. Problems 12 and 13 state, two identical masses at rest on a frictionless horizontal surface are connected to each other with an unstretched spring. Initially, the left mass located at the origin and the right mass located at x2 is equal to 1.0 meters. Then the right mass is pulled with a constant horizontal force of 100 newtons to the right. Eventually, the left mass shown is at location x1 is equal to 0.6 meters, and the right mass is at location x3 is equal to 3.2 meters. What is the translational kinetic energy of the system in the final state? Select the closest answer. So to solve this problem, we need to recall the definition of the translational kinetic energy. And in this case, we are going to use the force F net times the change in position about the center of mass. We know that F net in the x direction is equal to the force, which is equal to 100 newtons. So now we need to find our position about the center of mass, the change position. So to do that, I'm going to draw a quick sketch. The top half is going to denote our initial state. And suppose this rope I have here is our spring, for simplicity's sake. We have center of mass 1, let's call it that. And we have our final state, which is offset from that. And that will give us center of mass 2. So this will be 1 and 2, this will be 1 and 2. So this will start at x is equal to 0 meters. This will start at x is equal to 0.6 meters. This will end at 3.2 meters. And this will end at 1.0 meters. So to find our center of mass 1, it'll simply be the average of the two. So it'll be 0 plus 1.0 meters divided by 2, and that will give us 0.5 meters. And center mass 2 is equal to 0.6 plus 3.2 meters divided by 2, and that will give us 1.9 meters. So we can say our change in position about the center of mass is equal to 1.9 meters minus 0.5 meters, and that will give us 1.4 meters. So we can say the kinetic energy in our final state is equal to our F net of 100 newtons. I'll denote it in kilogram times meters per second squared times 1.4 meters. So that will give us an answer of 140 kilograms times meters squared per second squared. And that is also equivalent to 140 joules. This will correspond to answer choice B. Part B states, what is the change in internal energy of the system from initial to final state? Select the closest answer. So I'm going to define our system as our combined mass. So it's 1 plus 2 plus our spring. And our surroundings are applied force. That's acting to the right. So from that we can say the change in energy of the system is equal to the work done by surroundings. So we have translational kinetic energy, which we just calculated in part A, plus change in kinetic rotational, which in this case will be 0 because we don't have any angular velocity, plus our change in internal energy, which we're solving for in this problem, is equal to work surrounding. So that will be equal to 140 joules plus the change in internal energy is equal to the work surrounding is our applied force times the distance it is applied for. So we see from our previous part that the force is applied from x2 to x3. This is our distance that the force is applied from. So that will be equal to 3.2 minus 1.0. So this will be 3.2 minus 1.0 meters times the force. So we have 140 joules plus the change in internal energy is equal to our applied force, which is 100 newtons times 2.2 meters. So we have the change in internal energy is equal to 220 joules minus 140 joules, and that will give us 80 joules. And that will correspond to answer choice E. Problem 14 states, a sphere of mass m, radius r is given an initial angular speed omega I up an inclined plane. The sphere rolls without slipping and comes to rest at a height hf above its initial position. What is the sphere's angular speed omega when it reaches a height of h is equal to hf over 2 above its initial position? Note, moment of inertia of a sphere is I is equal to 2/5 mr squared. So we are going to choose an extended system for this question. Where our system is the sphere plus Earth. So from that, we know that energy of the system is equal to work surrounding. So we have translational kinetic energy, plus rotational kinetic energy, plus the change in internal energy is equal to F external times the change in distance of that force. In this case, we don't have any external forces, so that will cancel out to be 0. We know that the change in kinetic translational energy is equal to 1/2 times m v squared minus v initial squared. And change of kinetic energy, rotational, is equal to 1/2 times the inertia times omega squared minus omega initial squared. So, because we're also rolling without slipping, that implies that velocity is equal to omega r, the angular speed times the radius. So using that, we can rewrite our expression based on these given facts. 1/2 m r squared times omega squared minus omega initial for the translational kinetic energy, plus 1/2 times inertia, which were given to us as 2/2 mr squared times omega squared minus omega initial, plus the internal energy is equal to, let's see here, so it's mg, final height of h minus 0, so it's equal to mgh, and that will be all set equal to 0. So now that we have that, we can combine the first two terms here. So we get 7/10 mr squared omega squared minus omega initial squared plus mgh is equal to 0. And we can rearrange that so that we have 7/10 mr squared times omega initial squared is equal to mgh plus 7/10 mr squared omega squared. We're given at the highest point, HF, it comes to rest. So we can say that omega is equal to 0 at HF. So we can say mgh final is equal to 7/10 mr squared omega initial squared. So when you do at h is equal to hf over 2, you will get 7/10 mr squared omega squared plus 1/2 times 7/10 mr squared omega initial squared is equal to 7/10 mr squared omega initial squared. And so once we get that, we can simplify. We can move this term and subtract it from here. So that will give us that 7/10 mr squared omega squared is equal to 7/20 mr squared omega initial squared. So these terms will cancel out. So we get omega squared is equal to 1/2 omega initial squared. And we take the square root of both sides. You get that omega is equal to omega initial divided by root 2. And this will correspond to answer choice A. Problem 15 states, you lift a box of mass 0.5 kg off the table by pulling at a string through a hole at the top of the box by exerting constant upward vertical force of 13 newtons. When the box has been lifted a height of 0.20 meters off the table, the string has an unwound distance of 0.8 meters. What is the change in internal energy of the system at this instant? Select the closest answer. Use acceleration due to gravity is 10 meters per second squared. So first I'm going to identify our system and surroundings. Our system will be our box, and our surroundings will be our hand plus the earth. Now we can say that the change of energy of the system is equal to the work done by surroundings. But first, we have to identify our point particle, which is the center mass of the box. So we have that the translational kinetic energy is equal to F net times the change in the position about the center mass. So if we draw a quick free body diagram, we have gravity acting downward, mg, and we have our tension force by our hand acting upward, and I'll call that T, but it's equal to F. So we have that the translational kinetic energy is equal to F minus mg times the height h. It has gone up. From our previous equation, we can say that the translational kinetic energy plus the internal energy, the change of that, is equal to the work done by our hand plus the work done by gravity. And this is an extended system now. So now that we have that, we can further simplify that. So we have F minus mg times h plus our internal energy is equal to our tension force that we apply on the string times the change in RT plus work done by gravity, which is mg times the change in position so from that we have F minus mg times h plus change in internal energy is equal to Fd minus mg h, and this should be minus. And further, we can simplify that, so we have change in internal energy is equal to 13 newtons times 0.8 meters minus the mass, 0.5 kg, times gravity, 10 meters per second squared, times the height of 0.20 meters, and subtract that from 13 newtons minus mass times gravity times our height of 0.20 meters. And when we simplify that, we get that the change in internal energy is equal to approximately 7.80 joules. And this will correspond to answer choice E.